Because you can tell me the number 1, and I cannot find a number smaller than 1 that the function touches. That's the reason.
Yeah, makes sense. Thank you.
Awesome, my pleasure. How's it going? Oh, thank you. You want to just leave it here?
Yeah, I'll put it. This is the second time. This is my second time buying this one. Well, the first time I saw them in the I was like going to get them. They were gone.
I see.
They were gone like the moment passed over. By the time like I went outside and like.
No worries. Thank you for bringing it up, though. I appreciate it.
Yeah, I mean it's pretty.
Oh, sorry. Yeah, I just got for this.
You have so many like cool.
Oh, thank you. I have 10 of them, so new one every week.
Yeah, I was like, yeah, pretty awesome.
Thank you. Welcome, welcome. Hey. Alrighty, welcome everyone. Everyone find a seat. Let's get started at 2:31. Alright everyone, let's get started. So, how are we all doing today? Good. Awesome. This is a lot more energy than the first one. Actually, we've lost a bunch of people. I'm sorry if I'm scaring, I guess I'm scaring everyone off here. Hopefully not. Or maybe since the weekend is coming up soon. But, let's get into some calculus today. So, in particular, we're going to talk about the extreme value theorem, the mean value theorem, and then we'll do some assorted review if we have some time again. How does that sound? Good? Awesome. I'm so glad to hear. So, let's get started with the extreme value theorem here. Oh, and also I'll explain my shirt a little bit later as well because it is relevant today, actually. So, let's talk about the extreme value theorem. So, let's let f be a continuous function on the interval AB. Then, there exists C1 and C2 on the closed interval AB, such that f of C1 and f of C2 are absolute minimums and maximums of f on AB. And we can find these absolute mins and maxes by checking the critical points and the endpoints. Okay, so let's talk about what this theorem actually means. What it means is if we have some continuous function on this interval, we can define it find a minimum and a maximum. Okay, so this is actually very useful. This means we can use calculus to solve real-world problems when we're looking for mins and maxes. So let's try an example here. F of x is equal to x squared plus x plus 1 e to the x. And our problem said let's find all the local extrema, so extrema, minimum, maximum, on the interval -2 to 0. Now, this first example what we're going to do is going to be one where we use the extreme value theorem. So the extreme value theorem tells us that we have a continuous function. Why is it continuous? We have a polynomial, which is continuous, multiplied by an exponential, which is continuous. So the whole thing is going to be continuous. And also, we're looking on the closed interval -2, 0. So our extreme value theorem does guarantee there is a minimum and a maximum. So let's find it. So actually, let's write this down first. So f is continuous, and AB is closed. Actually, -2, 0 is closed. So this means we can apply our extreme value theorem. So let's take the derivative of f in order to find our critical points. Actually, let's just remind ourselves. What is a critical point? So a critical point, we say a is a critical point of the function f if f prime of a is equal to 0, or if f prime of a is undefined. Very good. Okay, we're more awake than the previous section this time. This is good. So critical point is if, so a is a critical point of the function f if f prime at a is equal to 0, or f prime of a, I'm just going to write does not exist, because f prime of a is a limit, so what we'll do is we'll find the critical numbers here. We'll say f prime of x is equal to, now we'll take this derivative here, so we'll have d dx of x squared plus x plus 1 times e to the x plus x squared plus x plus 1 times derivative of e to the x. So our derivative on the left side will be 2x plus 1 e to the x plus x squared plus x plus 1 e to the x. And now that we've taken this derivative, let's see if we can find those critical numbers. In order to find the solutions where our function is equal to 0, we need to find the points, we need to find the points where they're 0. So, this is why I'm really echoey. Am I less echoey now? Very good. So, in particular, let's factor out that e to the x. So we now have x squared plus 3x plus 2. And we can also factor, we have a trinomial, so we'll break it down into the product of linear factors, x plus 2 and x plus 1. So, someone just say bruh? Am I moving too quick? Oh no, you're just figuring it out. It's all good, it's all good. I have that reaction too when I'm doing math sometimes. So, alright, so we can read off these the solutions to this derivative equaling 0 by just looking at the solutions to the linear factors. In this case, we have that x is equal to -2 is a solution. X is equal to -1. And we have the factor e to the x. Does that contribute any solutions? No, because e to the x is never 0. So we have -2 and -1 are the points we need to check. And also remember our extreme value theorem says check the endpoints. So don't forget the endpoints. So we need to check the values x is equal to 0, -1, and -2. So let's look at f of x. So f of x, f at 0 is just going to, I drew this table the wrong way. Let's do it vertically. So x can be 0, -1, and -2. In which case f of x is going to be 0 squared minus 0. Sorry, 0 squared plus 0 plus 1. E to the 0, which is just +1. We have 1 squared, which is just 1, minus 1 plus 1 e to the -1. That's just 1 over e. And we have 2 squared is 4. Does anyone remember why 4 is the most terrifying number? Because because we're all 2 squared of it. So 4 minus 2 plus 1 e to the negative 2, 3e to the negative 2. And here now we can just read off our minimum and maximum values here. So which point is our maximum value? Yes? Yes, 0, 1, that's our point with the maximum value. So here's our maximum. Does anyone know what our minimum is? This one's tough. Well, 3 is bigger than e because e is 2.7, well, approximately 2.71. So negative 2 is going to be in between. It's going to be larger. So our 1 over e, that is going to be our minimum value. Okay, so we found our local max, or I guess global on this interval, and our global min on this interval. Does anyone have any questions about this procedure that we just did? No? Okay, so good. So we have our extreme value theorem, which tells us where our extreme values are. Now let's let's continue to talk about the extreme value theorem. I forgot about, oh yes, question. I'm sorry? Okay, so the question was, what is the point negative 2? So your question is x equal to negative 2, is that a local min or max? I'm going to say we have enough information to say it's neither. Does anyone want to take a guess? Why is x equal to 2 not local min or max? Yes? Yes, local min or max is going to be points where we have a small neighborhood around, or we shouldn't use the word neighborhood, because that actually means something in higher math. So we'll say all the nearby points are lower or larger, depending on if it's a local min or max, but negative 2 is an end point, so we don't have to worry about that. So yes. Yes, it's a local minimum, actually a global minimum on the interval negative 2 to 0. The point 0, 1, yes, that is an endpoint, precisely. Very good. Okay, so we just showed an example of using the extreme value theorem. Now, we're going to show an example now where the extreme value theorem does not work. Or, well, maybe it'll work. I just spoiled the answer. Okay, so here's my question. Here we have a function f given by this piecewise quadratic. We have a quadratic in 2 places. Remember, the mean value theorem, we have to ask whether f is continuous and also whether our interval is a closed interval. So first off, look at where f is defined. Do we have a closed interval? Okay, maybe we take a second to take a look at it. We look at the interval f is defined. So we're going from negative 1 up to 4. So is f defined on a closed interval? No, because we don't include negative 4. So already we have one problem. Okay, so now let's look at problem number 2. Is f continuous? Well, each of the pieces are quadratics. Those are continuous on their pieces. So the only place we could have a discontinuity is at the point 1. If we look at the top piece, 1 squared plus 1 is 2. On the bottom piece, negative 2 squared is negative 4, plus 4 is 0. So is f continuous at 1? No. So we failed both conclusions. Let's just write this one down. So f at 1 is equal to 1. Oh, nope. F at 1 is equal to 2. 1 plus 1 is 2. And as f approaches 1 from the positive direction, we approach the value 0. Okay, so we failed both conclusions, but let's still see. Because remember, the extreme value theorem is a one-way implication. If our conclusions hold, we guarantee a min and max, but just because our solution doesn't hold, doesn't mean f doesn't have a local min or max. I said that over and over again, or too many back and forths, too many negations. F can still have a max and a min, even if the hypotheses are not tested. Is that better? Yes, good. Okay, so let's try and look to see if f has a max and a min. We know how to graph our quadratics. Our first piece here, I'll draw that one in blue, or actually let's rewrite this question down. So we have f of x is equal to x squared plus 1 for x between -1 to 1. And we have negative x minus 3 squared plus 4 for x on the interval 1 to 4. So let's plot this. When x is equal to 0, that's going to be the vertex of the first piece. So when x is equal to 0, we're going to have 0, 1. Our quadratic is going to go upwards symmetrically, and it's going to reach the values +2 when x is -1 and +1. So we can connect these values of the parabola together. Next, we know that our parabola on this piece is going to have a vertex at the line x is equal to 3. Its y value is going to be 4 because at x is equal to 3 our quadratic term goes away. Our squared term, excuse me. And when x is equal to 1 plus, so when we're approaching x from x is equal to 1 from the right-hand side, we already said that the limit is going to be 0. So we have an open hole on this side. We also know that our parabolas are symmetric about the line going through the vertex. So on the right-hand side, we're just going to decay downwards like this until we hit an open hole at 4. At 4, 3, so it should be right up here, actually. Okay, so now the question is, does our function still have local extrema? Or sorry, absolute extrema? So here, does our function f have a global maximum? Yes. Yes. What x value does it happen at? 3, yes, we can see that right there. Now, does our function f have a global minimum? No. No. The reason why is because we can keep approaching 1. We can keep getting smaller and smaller values. Now, someone in the first tutorial, they asked me, they said, hey, why don't we just have the minimum at 1 with infinite 1.00, infinite many zeros, and then 1? Is anyone else wondering that right now? Okay, yes, that's what someone said. So here's the thing though. So that's not a number. Like if you have infinite many zeros, that's not a number, right? So what you could do, and a better way to think about local minimums and maximums is a value is a local minimum if you can tell me what the minimum is and I cannot find a smaller number. So for example, if we go back to our blue curve, x is equal to 0, that is a local minimum, just a local one. The reason why is you can tell me a y value. What's the y value? 1. And I cannot find a smaller value that the function touches. But if we were looking at the minimum here, or what we think is a minimum at x is equal to 1, if you say the number 0.05, well, I'll just say the number 0.005. So I can keep finding smaller numbers, so x is equal to 1 is not a global minimum. So this function has no global minimum. Is everyone okay with that? In general, whenever we have big theorems, so for example, remember we talked about IVT in week 3, we're talking about EVT and MVT this tutorial. Whenever we have big theorems, you should always ask, what happens if we remove some of our assumptions? So here, we removed the assumption that f is continuous, we removed the assumption that our interval is closed, and we're seeing now our theorem fails. We're going to do the same exercise every time we see theorem fails. Yes?
So when you mentioned that you could
So whenever we do math with the infinitely large, the infinitely small, approaching infinitely close, this is getting into the field of analysis. So I would suggest in particular, real analysis is a really cool kind of area of study. So if you like calculus, you can continue on with upper year math questions. Yes? We don't worry about that for most of this course. It's too much to think about. And often we would want to study other topological properties and other stuff like that without using it. So usually we just ignore them. Okay. There's another question somewhere here as well. I lost it though. Maybe not. Okay, so very good. Shall we keep going? So okay, this is here. So D. Let's talk about the mean value theorem. Not mean as in angry, although that's what my shirt would, that's my shirt today, the mean value theorem. So, given an interval AB and a function f, which is continuous on the closed interval AB, differentiable on the open interval AB, then there exists some c on the closed interval AB with f prime of c equals to f of b minus f of a over b minus. Okay, this equation is complicated. So what does it mean in real language? Well, what it means is there's a point where the instantaneous velocity is equal to the average velocity. We can think of it like this. So imagine I'm running late for this tutorial. I want to drive. I want to come get here. I want to come get here quick. Okay? While I'm on my drive, I'm going to average. Maybe it takes, maybe I'm 50 kilometers away and it takes me an hour to drive. So I'm averaging 50 kilometers an hour. But I'm not moving at 50 kilometers an hour during the entire time, right? Maybe I'm 80 kilometers an hour on the highway. I'm 0 kilometers an hour when I'm at a red light. What this theorem says is, at some point between, I will be driving at exactly 50 kilometers an hour. That makes sense? And that just comes from our smooth changing from 0 up to 80. It's because we don't have any of those big jumps, any teleportations in our derivative here. Okay, so let's take a look at this. So, oh, by the way, if you can't see my shirt, this is the drawing that's on my shirt right now. It's the mean value theorem and the nice value theorem. Ah, very good. Okay, so let's do some applications of the mean value theorem. Okay, so Kira. Is Kira here? Ah, no worries. Okay, well, so anyways, I was looking through the survey, and this was included verbatim, and I thought, wow, this is hilarious. So, Kira loves gravity, and it keeps falling for her. Very good. So, Kira tests out gravity by jumping off a 30-centimeter tall step, and follows the trajectory of the function h of t is equal to 30 minus 5 over 6t squared, landing softly on the ground at t is equal to 6. And the question says, at what point are the conclusions of the mean value theorem satisfied on the interval 0, 6? Okay, so let's draw this situation here. So here we have our steps. Here this is 30 centimeters. And here is our jump, touching the ground at time t is equal to 6. Okay, so let's verify. First off, in our hypotheses for our mean value theorem, is h continuous? Yes, because a polynomial function, in particular its quadratic, is continuous. Also, h is differentiable. Why is h differentiable? For the same reason, a quadratic function is going to be differentiable. In fact, polynomials are differentiable. And we have a closed interval 0, 6. So because of these, we can apply the mean value theorem. So by that, there exists a point C on the interval 0, 6, such that h prime of c is equal to h of 6 minus h of 0 over 6 minus 0. Okay, so we already said h of 6 is going to be 0. We could plug that in, or sorry, yeah, h of 6, we plug it into our function. Our t's cancel, 5 times 6 is 30, so 30 minus 30 is 0. So h of 6 is 0, we're touching the ground, and h of 0 is 30 over 6, so h prime of c is negative 5. Now, the thing is, we know what our function h is. And our question says, at what point does the conclusion of the MBT get satisfied? So we're asking for what point is our derivative equal to negative 5? So let's do this. Let's take the derivative of this function. The derivative h prime of t is equal to, from our power rule, negative 5/3 t. So we'll plug that in, negative 5/3 t, and we get the answer that t is equal to 3. So, at the point 3, our average velocity will be the exact same as our instantaneous velocity. Is everyone happy with this question? Okay. These mean value theorem questions often are tricky, and I get a lot of questions about them. So we're going to do a couple different versions of these. In particular, B and C are going to be the ones we're going to watch out for. So let's do part B. Owen, is Owen here? Owen, you run for the cross-country team. Very nice. Is that varsity, or is that like do you have any meets or any races? That is super exciting. So Owen runs for the team, and right now Owen he was preparing for a race on the way here, right? So you were in BSC beforehand at 121, which is 5 hectometers in the start line. And at 130 is in the 1Z83 tutorial at MDCL. And runs at a speed of at least 10 hectometers per minute until arriving right outside. So, what is the closest distance that MDCL can be from the start? So, let's say this is our start line here. Let's say this is BSB, and this is 5 hectometers. And this over here is MDCL. Okay. 10 hectometers per minute, that's really 10 hectometers, that's a kilometer. That's not reasonable. You're really fast. A kilometer a minute, you're really fast. So let's let F be the distance in minutes. Minutes after 1 p.m. So in this case, we have, by our mean value theorem, we know that our distance is going to be a continuous function, and our derivative, which is just velocity, that's also continuous, and we're looking at a closed interval from 21 up to 30. So let's apply our mean value theorem. That means there exists C such that f prime of c is equal to f of 30 minus f of 21 over 30 minus 21. Now let's plug in this information. We know that f of 21 is 5, and we know that 30 minus 21 is 9. And we have f of 30. Now the other thing we know is that f prime of c is always bigger than 10. So if f prime of c is always bigger than 10, we can isolate and find the minimum value of f of 30. So f of 30 minus 5 is bigger than 90, and we add 5 to both sides. F of 30 is bigger than 95. So MDCL can be at minimum 95 hectometers from the start of the race. Very good. So, what questions do we have about this one? Oh, yes, questions. Can we start? Yeah, can we recap the part where we set up the derivative? this line right here. So we got this line from the mean value theorem. Is this okay so far? This is exactly what the mean value theorem says. Then, from this line to this line, we plugged in our numbers from the question. And then from this to this inequality, how did we get here? We know that the derivative is always bigger than 10. Here, 10 hectometers per minute. So the derivative is always bigger than 10. F prime of c is always bigger than 10. Then all we did was we moved around our inequalities. So what I will say is the word problem might have made it a little bit more confusing, but this will be very similar to one of your child's math homeworks that you'll be happy to have it this week or sorry? October 11th? Is that right? I didn't see any October 11th. Because that's I don't think the 11th, right? We're a little bit ahead, but that's okay. Thank you for. I'm glad. Okay, very good. So let's do one more mean value theorem. This is normally a question I got a lot of emails about. So let's look at this right now. Let's let f be a function whose graph is shown below. We'll estimate the two values of c that satisfy the conclusion of the mean value theorem on the interval 2, 7. Okay, so let's check. Before we apply our mean value theorem, 2, 7 is a closed interval. Our function f is continuous everywhere because we can draw without taking our pen off the paper, and it's differentiable. Why is it differentiable? Yes? No. No. Continuous functions don't have to be differentiable. For example, the absolute value function. So, the reason was, it's actually the other way around. If a function is differentiable, it has to be continuous. So why is this function differentiable? Yes? Sorry? So we don't know if it's a polynomial function. We can guess it looks like a cubic, but we don't know it's polynomial. So why is it differentiable? Sorry? Look at the vertical line. No, that just means it's a function. If it doesn't cross two vertical points. So why is this differentiable? Yes? Yeah. Yes! There exists a tangent line. Our function b can be approximated by a tangent line. So that's why it's differentiable. Okay, this is important. This is from week 2 and week 3. So everyone remember, this function is that what you're going to say as well? Yeah, very good. So this function is differentiable because we can draw a tangent line. So let's try and use the mean value theorem to on the interval 2, 7. So here is our closed interval. This is 2. X is equal to 2. Here's x is equal to 7. And we want to find points where our average slope is equal to our instantaneous slope. So here our average slope is given by this line right here, the slope of that line. How do we find our instantaneous slope? This is literally what I would recommend doing for this question, because it's hard to read the values from the graph. Copy paste this line, like do this on a tablet, copy paste the line, move it up and down. Wherever you see its tangent, that's the point. So for example, if we move the function, the line up and down like this, here, this point, this line is parallel. So that happens at the point 2.75. We can also look one other place. Where is it parallel? Here, at 5.75. Okay? Approximately. So, do this exactly. Just move your function up and down. Do not try and find an equation for this. Don't try and find the function in explicit form. Don't try and do any of that too much. Just find the slope by moving it upward. Okay, very good. Okay, Daniel loves to play hockey. Is Daniel here? How's it going, Daniel? So Daniel loves to play hockey. What position do you play? Center, very good. So you're going to be on a breakaway then. So Daniel's on a breakaway, a stick handling the puck back and forth. Let f of t represent the position of the puck in meters from the board on the south side of the rink. And the derivative of the movement of the hockey stick f is given by f prime of t is equal to this polynomial function right here. The question says let's find the t coordinates of the local maximum points of f, and that is the times at which Daniel is closest to the north side of the rink. So all we have to worry about here is we have a derivative. What are the local maximum points of f? So let's find the local maximum points of f. So in particular, remember, from our theorem, from our extreme value theorem, we need to find the critical points. And then we're going to use the first derivative test to find the actual values. So from our critical points, remember, those are the points at which our derivative f prime of x is equal to 0, or undefined, or it does not exist, exactly. But there are no points where it won't exist because our derivative is a polynomial function. So let's just find the zeros. What's nice is we can read the zeros straight off the graph. So if f prime of t is 0, that tells us that t is 0, 2, 3, or 4. The solutions are just the solutions for all of the linear factors. So now what we're going to do is find the behavior of f prime when we're between the critical points. So let's look at these intervals. We're going to make a little chart here. I heard some groans about the chart. Is that correct? Or no? So 0, 2, 2, 3, 3, 4, 4, infinity. Now, okay, what we care about is we care about the sign of f prime. Yeah, I hear a lot of murmuring. Do we have any questions before we continue? Or did I make any mistakes? Yeah. Scroll to the left, yes. Sorry, to the right? To the left? Better? Okay, so we are interested in the sign of f. The sign meaning whether it's positive or negative. Notice that our t to the power of 8, that is always positive. So what we care about is the sign of the linear factors t minus 2, t minus 3, and t minus 4. So between negative infinity and 0, our sign of all of these is negative. Between 0 and 2, all of them are still negative. Between 2 and 3, our first factor is going to be positive. So between 2 and 3, t minus 2 is positive, but the other two factors are still negative. Between 3 and 4, our first two factors are going to be positive, and our last factor is going to be negative. And finally, between 4 and infinity, our first three factors, all of them are going to be positive. So that means that f prime of t, remember we can multiply negatives and positives together. If we have an odd number of negatives, it stays negative. If we have an even number of negatives, it turns positive. So this is f prime. So what happens to f of t? When it's negative, f of t is going to be decreasing. When it's positive, f of t is going to be increasing. And now that we have this behavior, we can read off which point is a local maximum of f. 3. Are we sure? We didn't seem so sure. What point is a local maximum of f? 3. There we go. Am I getting annoying with am I asking too many? This is good. We want to stay engaged. So this is a local maximum. We also have local minimums at x is equal to 2 and x is equal to 4. And I asked this question in the first tutorial, but I don't know if this has been introduced yet. What type of point is x is equal to 0? Yeah.
Point of inflection.
Point of inflection. I don't think so. Point of inflection is normally when the concavity changes. So we don't think we know enough to know yet that it's a point of inflection. Yes. Is it sorry? Asymptote? No, so an asymptote is when our function goes to infinity. Yes? Why did we put t is equal to 0? Sorry. Yes, in the back? A point of equivalence. I don't think I've heard that before. Yes, it does behave like x to the 3. You're right. It behaves like x to the 3, but it has a name. Saddle. Yes, very good. This is called a saddle point. So this is a saddle. Very good. Can you remind me your name? V? Very nice, V. Very good. So, challenge question. Okay. Oh, yes, question. What is a saddle point? So, you know how cubics, they go up, they rise, they come to a critical point, and then they keep going back up. That is a saddle. A saddle is a point where it's not a local minimum or a maximum, but we're still attaining a derivative of 0. So it looks like a cubic behavior. If that's scary and we don't need to know what it's called, like if it's scary and you haven't been introduced to it yet, then don't worry. Okay, we're going to do one example which is also scary. You guys aren't going to get scared off if I do something that looks a little bit complicated, are you? No? Okay, very good. So, we're going to do one proof. Just one, just one. It's okay, we'll get our feet wet, and maybe this will help us decide if we want to take more math courses in the future. So, let's verify that the equation e to the x equals b admits exactly one root. Oh my gosh, how do we show that it has exactly one? Well, let's show that there's at least one, and then we'll show that it's impossible to have more than one. Good? This all is sensible. So what's the value of x that makes e to the x equal to b? Ln of b, yes, very good. So here, show that there's one root. Well, our root is x is equal to ln of b. Okay, so how do we show that it's impossible to have more than one root? Let's suppose that there were two roots. Let's call those two roots c and d. Or no, let's call them c1 and c2. So here, by the way, let's let f of x equal e to the x, just for simplicity. So suppose that there are two roots to this equation. That means that there are 2 points, e to the c1 equals e to the c2 is equal to b. This is good so far, right? We're assuming that there are two roots, c1 and c2, which both equal, when we plug it into f, equal b. Now, remember our mean value theorem or our Rolle's theorem. Since this is continuous and differentiable, by our Rolle's theorem, there exists a point called D between C1 and C2 such that f prime of D is equal to f of C1 minus f of C2 over C1 minus C2. Is this okay so far? We're just using our mean value theorem or our Rolle's theorem. So f of C1 minus f of C2, that's just b minus b. So this f prime of d is 0. So that means that there exists some point where f prime of d is 0. Okay, what is f prime of d? What is f prime of d? It's e to the x, or plugged in at d. F prime at d is e to the d. But is it possible for there to be a point d such that e to the d is 0? No. So actually, it was impossible that we had 2 roots. So this is impossible. So we must have had exactly 1 root. Okay. Is everyone okay with what we did here? How we went from step by step? Yes. Well, if there are 3, then there's at least 2. So we're letting C1 and C2 be those 2. So this proof wasn't too scary, right? So who wants to take more math? Yes, very good. So anyone taking, is anyone comp sci taking one discrete math next term? Very good. So this is called a proof by contradiction. So keep this in your back pocket. Okay, we're going to do... Okay, this is just a cool fact. Oh, by the way, this challenge question is homework. In this one, this is actually even more fun of a question. How do we show that there is 1 root? You're going to need to use something. You could use IBT for this. Yeah, use IBT for this. This is good. Review your week 2. Please do this question. Out of all of the homeworks, this one's the best one to do. Okay, this one is a very cool example. We'll do this together. Is anyone in physics right now? I'm looking at you engineers. Very good. This will be a fun question. So, let's consider a circle with radius 1 centered at the origin. We're going to find an expression for the slope of the tangent line, and then we'll do part B after. So, does anyone remember what is the equation of a circle? Yeah. Yes. Yes, equals radius squared. Or here, because we know radius is 1, x squared plus y squared equals 1. So, question A says find a derivative, or, I spoiled it. Find an expression for the slope of the tangent line. That's just the derivative dy dx. So we'll take the derivative on both sides, d dx. On the left, we're going to get 2x plus 2y. Is 2y it? dy dx, thank you, equals derivative of 1 is 0. So we'll isolate for both sides. We'll get 2y dy dx is equal to negative 2x, or dy dx is equal to negative y over x. Negative x over y. So we'll draw our circle. And what this basically says is at any point P, the slope of this tangent line right here, this slope is negative x over y. Okay, so now question B says, consider a tangent line consider a line tangent to the... Oh, yes, okay, that is the line. So this is blue, the tangent line. What is the angle that the tangent line makes with the ray from the origin to P? So the ray from the origin to P, that is this orange line here. Now, what is the slope of that orange line? So, hold on. So, the slope of the blue line is negative x over y. Our orange line goes to the origin. Remember, the slope of our orange line is going to be y, is rise over run. So, what's the slope of our orange line? Yeah? No, the orange line. The orange line, the slope of the orange line is the rise over run, right? So the slope of the orange line is, I heard it, y over x, yes. So the slope of our orange line is y over x. So notice, these slopes are negative reciprocals of each other. We know that negative reciprocal lines, now this is where you're going, negative reciprocal slopes mean that the lines are perpendicular, very good. And if they're perpendicular, then they intersect at what angle? At 90? At pi over 2, right? I'm just joking. At 90 degrees, you're correct. Or at pi over 2 radians. But, so yeah, they intersect at a right angle. Which means that, oh, I put degrees in the answers. Okay, fine. You guys get a pass on that one. You get a pass on that one. That was my mistake. But the point is, so let's look it back to those people who are in physics. You ever look at your acceleration, you wonder why, if you have a motion over a circle, why your acceleration points directly towards the center of the circle. This is why. Isn't that cool? Okay, so it's 3:18. Do you want to do one more example, or do we want to call it here? Call it here? Is that what everyone's saying? All right. Thank you, everyone, for coming. Next week, we're going to do... Next week, we're going to come back, do some more derivative applications and some test review. Thanks so much. Hello, how's it going? I'm just gonna leave this up actually.
Oh, okay.
Leave it up. Alright, let's see. I guess that is one not so great thing with these word problems. I'm trying to squeeze in questions. Yeah, I'm trying to squeeze in questions that have people in them because I think it's kind of fun, but as a side effect, unfortunately, it makes these things not so great, but that's okay.
This happens in like every course of me with word problems. I read them, I'm like, wow, what a great story. What a great story are you doing?
That's pretty funny, actually.
Man, I love your shirt, Bobby.
Oh, thank you very much. Look up for next week. It'll be new next time.
I will.
So, let's see. So, what's important here, I guess, okay, this is something, thank you for coming. This is something we don't talk about that we kind of assume is that we know the derivative, thanks for coming, the derivative of your distance is your velocity, right?
Oh, yeah.
So that's something we're not taking into account. So here, we run at a speed of 10 kilometers per minute. This is just saying our derivative is at least 10. That's where we got. So you see here, 10 hectometers per minute. At least, so our derivative is always bigger than 10. That's where we got it from. And then here, we're actually missing a divided by 9.
Oh, okay. Oh.
From our mean value.
Yeah, that is my problem. I see.
But does that make more sense? I think this is the tricky part, the derivative being bigger than 10. Is that right? Or which part is tricky?
I'm just wondering, like, more or less, because he's running. I think I'm just trying to conceptualize it too much in the realm of physics that I'm like forgetting that this is just straight calculus. So he's trying to run to BSB, and then he's running. So he starts at BSB and he's running to NBCL. He has to run from BSB to NBCL within 9 minutes.
Yes.
And he runs at a speed of at least 10 hectometers per minute, which means his velocity is always above 10. Which means